right, good morning everyone. My name is Romain Fleury and I'll be chairing the morning session today. So the first speaker will be Wolfram Pernice from Heidelberg University, and he will be speaking about opportunities for photonic computing.
All right. Thank you, Romain, very much for the kind introduction, and also thank you, Clara and Florian, for inviting me here to speak a little bit about photonics. Yeah, I'm very happy to share our insights into this field, and I'd like to discuss a little bit where this could go, or where the challenges are for these integrated systems. So we work on chip-based computing approaches that we fiber couple, and we try to use those for arithmetic, very basic ones, but also with the long-term goal of scaling this, in particular for AI, it's probably everyone in this field. And we think photonics is interesting because it may be a long-term perspective for making systems bigger. As you all know, the current approaches for making AI compute larger are mostly based on digital electronics, and there the scaling potential lies in essentially making the chips bigger. So more silicon gives you more transistors, and smaller transistors give you higher density. And if you make this bigger and bigger, then in principle you can also build bigger and bigger systems, despite reaching sort of the physical limits of what these structures can look like. So this is one of the latest foundry processes by TSMC, 1.6 nanometer CMOS. That means that the gate length of these transistors is about 3 atoms, so can make a little bit smaller, but not much. And therefore, the way to get more compute is basically by joining a lot of these processors together. And this way you get a lot of transistors. So one of the latest GPUs that came out by NVIDIA earlier this year has more than 300 billion transistors. So that's more than 10 times what the brain has in neurons, a very, very big chip. And you can imagine that this can go on for some time, but not forever, in particular if you don't think for the next 10 years, but more 30, 40 years or so further in the future. And I think this is where photonics or optical systems have a place, since they're already quite established as well, maybe not as densely integrated as silicon digital electronics, but nevertheless, there has also been a lot of progress in silicon photonics in establishing the building blocks for making complex circuits, mostly for communication, but also at scale. So you can produce these types of systems on a wafer level, make also hundreds or thousands of devices. Complex photonic integrated circuits have more than 10,000 components already these days, and this can be made larger too. To date, they mostly operate digitally, so you use them for transmitting data, and there are detectors for such communications, modulators, and also amplifiers for keeping the signal alive. So basically everything is there, but it's mostly used in a digital fashion, so you transmit zeros and ones as you require for data communication. And hence, by relaxing this requirement a bit and going away from digital to analog photonics, you also transition into a range where you can do computation by performing analog operations on these systems, and also using them potentially at scale by just taking this approach and using it for analog computing, which is sort of what we are interested in. So in principle, you use exactly the same components. So we also have some modulators for encoding information. This is also driven by CMOS electronics. As always, optics is good for something, but the hard work is still mostly done in the electronic domain. You also need to make sure that you can convert efficiently between digital and analog, which is challenging. But nevertheless, all the building blocks are there for making this also potentially large. The main challenge that we face is basically by taking all these nice components that we already have and making them or combining them into a system. So basically, the chip is one thing, but there is a lot of periphery around it, and this is also sort of how we started. This is one of our first optical computers that we built. That's it, some basic arithmetic. There is a chip somewhere here on the chip, but it's really the smallest part. Most of it is periphery, so multiplexers for joining signals, a lot of detectors. Those are these guys here, polarization controllers, amplifiers, and so forth. But really, the chip is the smallest part. And also, this system is big and convoluted. There's more than 300 meters of fibers and lots of connectors. So our challenge has always been to take this thing and bringing it down to a chip so that you can actually use it as a GPU. And only in recent years this was somewhat manageable, but of course nowhere close to the systems that you have seen on the digital side. So the GPUs and others, since they have a lot more components than we currently can build. Nevertheless, this is our challenge, and I'll tell you a little bit how we get arithmetic into these systems. So everything starts with chip design. This is a nicely photoshopped image by one of my students of a gallery of the different chip designs that we have made in the last years. You see there are some simpler ones and some more complex ones. There are also different platforms. Some of them are for indium phosphide, others for silicon, others for silicon nitride that we can make in-house. And we, in principle, design these on the computer. We simulate them and try to make sure that they perform the optical operations that we want to have in the end. With this design, we then either go to the clean room or to a foundry. So this is one chip example that we made ourselves in Münster, actually. This is a silicon nitride system, which also has more than 10,000 components, but it's not one system. It's a lot of little circuits that have different parameter scans and so forth. This is typically 15 by 15 millimeter in size, so the size of a thumbnail or so. And these sort of systems with a few layers of lithography we can make very nicely in our clean room after the processes have been optimized and you spend some time in getting everything right. However, this is mostly a passive chip, so anything active we need to add externally. We need to couple a laser source to there, need to couple detectors, modulators, and so forth. And mostly what this chip does is some sort of signal routing, multiplexing, and all the passive functionality that you need for preparation for compute. If we want to go to these real active systems, we don't build them ourselves anymore, but we send them out to a foundry. So this is a silicon chip that was made at IMEC. This has now also active elements, these modulators, detectors, no lasers, but at least all the other periphery that occupied most of the table. And this way you can already make this quite a bit smaller and in principle also scalable, since this is realized also on a wafer level, and you don't just get a single hero chip as this one, but maybe 20 or 30 in the same go. A challenge that we also had for a long time is to talk to these systems efficiently. So I think from the industry perspective, this is also one of the key challenges in photonics, basically fiber to chip coupling, especially if you think about large-scale systems where you want to really get most of the light in and not lose much. And our solution to this challenge, basically the mismatch between a waveguide and an optical fiber, to bridge this in a reproducible way, has been to use 3D laser printing for making these sort of adiabatic interfaces that direct light from out of plane into the plane and also focus it more towards the size of a waveguide. So the principle is basically that we exploit total internal reflection here at this back surface of this 3D structure. This way you can direct a beam coming from a fiber in plane and focus it down towards a waveguide with this taper structure. And at the same time you can compensate for the divergence of the beam coming out of the fiber array or so by adding this lens structure here, so that in principle you can get a pretty good coupling efficiency. You have a question?
Yeah. What's the typical coupling rate?
I'll have it on the next slide. So they can be very good. There are, of course, also losses. You have Fresnel reflections here. There are scattering losses here at the surface, so it's not perfectly smooth, but pretty smooth. And by playing different tricks with adiabaticity and also the cladding of the material can at least reduce those quite a bit. Yeah, I'll show you the measurements in a second. The other challenge that we had is to do this at scale again. So we don't just want to connect the one hero device, but ideally all of them on the wafer surface. And this works with a nice tool that we got from Nanoscribe, since it can do automatic alignment, so recognize these little markers here, and then position each of these couplers at the right spot, and do this also in a relatively fast fashion. Now, the devices that came out here for 1550 for the silicon nitride chip are pretty good. So the best coupling losses here are on the area of 0.5 dB per coupler. This is, of course, corrected for Fresnel and coupler losses and so forth. But in principle, you can see that with this system, you can get relatively good coupling efficiency and also relatively broad band. So this is about 100 nanometers in bandwidth. And here the transmission is more or less flat. This is very nice if we want to work in these wavelengths multiplexed regions and also think about coupling a lot of different wavelengths into the system. And this is enabled by this align structure from Nanoscribe, which can basically do this more or less by itself once you have the process established. There is a lot of background work needed, but in principle, it can do this once the process is established. Another challenge is to basically do this not for a single chip, but also for many chips. So therefore, we started also looking into packaging using this assembly robot here. This is a machine we got last year from Tech, which in principle can do this also automatic. So it is able to grab a fiber array, position it actively relative to the chip, and then glue it automatically there. So this would be the way to not just make a single chip, but also a lot of them, and therefore have a reliable way of fiber coupling entire systems and not just measure as we usually do on a manual stage and just go from device to device. Because in the end, if you want to do distributed systems, you don't just need the one chip, but maybe hundreds or maybe thousands, not in a uni, but elsewhere. And for this, all these processes need to be automized as well. Now, once this all works, you get very nice systems out of this. This is one example of a packaged chip. So again, here's the silicon photonics strip line, this time not from IMEC, but AMF in Singapore. The fiber array is glued here on top. This thing here is so that the tool can actually pick it up. It's not a mechanical functionality, but it's just so that the area is large enough that the vacuum gripper can actually collect it. And you can also see that you can electrically connect it nicely to the underlying PCB with quite a number of connections. So this way you have optical access to the chip, and at the same time also electrical access to the chip. And then in principle, you're in business and can start measuring. Okay, on this chip, we built these photonic arithmetic units, so basically mathematical matrices. So this is what we have been doing in the past, building these crossbar arrays, where we perform essentially two operations. We do addition. This is basically joining two waveguides together at intersections to adding signals onto a common bus. So here you see these joining elements, these directional couplers, which basically add light coming from different laser sources onto a common output waveguide, where we can then perform the actual calculation, which is detection with a photodetector. This one would be on a chip, this one not. And the other element that we have here are modulators. So whatever device that can attenuate a signal, this performs multiplication by attenuating an input intensity by a fixed amount. This way you multiply two numbers, and the result is basically the power that comes out in the end. And if you perform this in one of these columns here, then basically you calculated vector product of the vector inputs times these encoded transmission vector, and therefore do a very simple scalar product for this particular detector. This is the chip itself that implements this abstract concept on a silicon device. So here again, you see this crossbar array with 3 columns and 9 rows, or the other way around. So at the output, we have 3 photodetectors. So we perform 3 scalar products at the same time. And the input here is provided by 9 inputs. In this case, not 3D couplers, since the foundry cannot make those, but grating couplers. But nevertheless, you can still glue the fiber array into this coupling region and then talk to the system. Okay, what did we do with this chip? Well, we basically did steps that I just mentioned. So get the chip from the foundry, attach the fiber array, put it on a PCB, and then the rest is this, what the physicists like to call just engineering, building this big box. And this is basically the biggest part of the entire project, since this really is a big effort. So designing the PCBs takes a lot of time. Programming the FPGA here that drives everything takes a lot of time. It's very complicated. Doing all of this at high frequency is even more complicated, and high frequency here is not even very high frequency. It's a few gigahertz, so not faster than a normal CPU, actually more or less the same speed, but nevertheless, this is all a lot of effort. And if you do this over many years, we can arrive at this box, which is sort of a 19-inch format, so size of a desktop computer, but inside the heart is called sort of this photonic chip. But yeah, this is a lot of interfacing and a lot of technical design, which I would say is always the bulk part of this whole work. And you have to do this for every new system over and over, since each chip that we built is different. So yeah, everything changes from device to device. And we have spent quite some time to design this into a more modular system that you can only replace the silicon chip, but keep the periphery. And this works to some degree, or hopefully in the coming month or so. On there, you need then to run a system. So this is the other part that needs to be done, basically programming the access. So the photonic part does only this particular bit here, analog multiplication and addition. And then you need to feed it somehow from an external source. So it needs also a digital front end. This is the FPGA that I mentioned. In there we can send data into this, prepare it so that it matches the DACs and ADCs on the box. It sends it to the photonic system, reads it out again, and converts it back to the digital domain. And then you can wrap this into a Python framework that you can actually talk to it and then embed it into your preferred classification algorithm. And in the end, it will allow you to do also some basic arithmetic, but it's computed on this box in the analog domain with all its pros and cons. What this one currently can do is basically run all optical neural nets, not very big ones, but nevertheless, some of them where all the multiplications and vector matrix products are done on the box. The rest is done in digital. And this way you can do classification of M is pretty good, also with CIFAR, not as good, but nevertheless, it works. And therefore, we are quite happy with the system. Yeah, this is what we have been doing for quite some time. And then recently we also asked ourselves, well, what's happening if we want to really make this bigger into a system that can compete with the GPU? And then it gets interesting. So from a very abstract perspective, what we built here are linear photonic processors. So this is the optical domain. And then you need to make sure that it can talk with the rest of the world. So this is the electronic domain. So you need some input with a certain precision, say 8-bit, which is already quite high for analog photonics. You need to convert this into analog values with DACs, read it out with photodetectors, and go back into the digital domain. So there will be some noise, there will be some drift, there will be some imprecision, there will also be losses and power consumption and so forth. And then the big question is it worth all the effort? So what we did is, this is a very messy plot. I apologize, but I'll go through it. So what we did is we looked at different types of these linear processors and thought, well, how big can you make them? And if you make them bigger, how efficient can they be? So one example here are these weight banks that Paul Prusmal, for example, is building by this broadcast and distribute approach with tunable ring resonators. And what we looked at is the overall performance that you can get from a system if you make these matrices bigger and bigger, and then calculate all the power that is dissipated in the DACs and the ADCs, in the driving electronics, and also in the photonic systems. And what you can see here for this particular implementation, if you have volatile or non-volatile weights and make them larger and larger, it scales pretty well. So for matrix sizes that are larger than 100 by 100 or so, you can get relatively good efficiency in terms of tera operations per watt. So this is one of the metrics that are used. Yeah.
What is the state of the art in typical architectures for this type of metric?
It depends on what you call the state of the art. So if you take a fast GPU, for example, and you work with not with sparse matrices also, then you get about 8 TOPS per watt. This is what NVIDIA promises. If you take a real matrix, then it is a lot worse, factor 1,000 or so. If you go to, say, the light matter system from early last year or so, this is about 1 TOPS per watt on this order. So yeah, it really depends. Also, there's a big difference whether you just look at the pure compute system that is done in the optical domain. You can get lots of TOPS very cheaply if you don't have the driving electronics and just use some fast AWG or so. If you build an entire system again with the ADCs and DACs and everything, then it's typically a lot less, because then you have this just engineering problem, which basically kills a lot of it. So I think state of the art sort of is 10 TOPS per watt. This is, for example, the Hermes system by IBM. There are also some others, but sort of this is where you can go. And you can see here, if you have non-volatile weights, which you usually have, this is also sort of the baseline that you can get with that system. Another one we looked at are these MZI meshes. Probably Dirk told you about them yesterday. Maybe not, I don't know. This is also a very nice approach, but it has this problem that it only scales to a certain degree, and at some point the insertion loss of each component starts to kill you. So you can get a little, around 10 TOPS per watt or so with the right weights as well, and then there is a steep drop off because you throw way too much optical power. But still, about 10 TOPS per watt. And now the interesting one is that we work with, this is very sad, since here the efficiency is 10 to the minus 1 TOPS per watt. So no matter what you do, this will never be a very good system for scaling. So should we really do this? I don't know. From engineering and testing point of view, it's a very forgiving system since it's not so hard to build. But if you really want to build a useful computer out of it, this is probably not your best shot.
What's the fundamental mechanism that makes the edge drop filter based approach more scalable?
In principle, what makes it scalable is if you build good rings, you do not lose a lot of power since you drop everything onto the other side. So if your coupling is designed very carefully, then you can preserve most of the power. Your challenge is basically that you need to fit all these resonances into the free spectral range of the ring. So that means you would have to make very small ones for a lot of wavelengths, which again is not so good for the ring performance. So in practice, there are of course trade-offs. But this was more looking at what can you do if you make a system very good.
So this calculations, the per watt, the watt includes everything?
That includes everything, yeah. Yeah, so we took state-of-the-art values for DACs and ADCs, so admittedly very good ones, but nevertheless someone built them. And then it includes the laser power and the losses and whatever. Also the driving CPUs, this is just an offset. But in principle, it gives you at least an order of magnitude idea of what is helpful. So they all can compete with digital electronics, but it's hard to do much better. There is, however, another way, and this is using an approach that also other people have looked at. David Moss, for example, but also others before this time wavelength interleaving. This is here a nice sketch how this works by one of the PhD students. I'll explain it in a little bit. So in principle, what you do is the central idea is that you exploit the frequency domain and the time domain at the same time. So you encode your weights in the frequency domain in spectral channels. And then all of these spectral channels are multiplied in the time domain at the same time, which is what makes it efficient. And then you use dispersion, which you have in different devices to basically pull the time signals apart again and align different frequencies with different time bins. And then if you encode your data across this in the right way, in principle, you can devise systems that also scale longer term. Yeah, it's maybe not so easy to understand, so he made another one that I'll run you through it. So assume we have three different frequencies, so blue, green, and yellow. So those would be the three different weights. Those are multiplied in the time domains with different amplitudes, the same way as in the crossbar. So all happens in one instance, but you get different vectors added on top of that. Then comes the trick, which is dispersion. So you basically use a long fiber or other element to basically pull different wavelengths apart. And because they travel at different speeds, different wavelengths will appear at different time slots. And as long as your fiber is long enough, you can offset exactly by one time slot that is given by your modulation frequency. So that basically means that your signals are shifted in time by exactly one time bin. And then if you fill your pipeline and wait till time slot 3 here, if we work with 3 wavelengths, then all of them align again. So the green, yellow, and blue one, but they're multiplied with 3 different amplitudes. So this way you also multiply a time vector with a frequency input and can calculate the summation in one time slot. So this can be fast. And if you have a lot of wavelengths, you can also scale this to a lot of channels with not a lot of loss. So what this does is basically calculates the scalar product, x vector times w vector. And then what it is a convolution in the frequency domain. Okay, so this we built first with off-chip components. So what you need is a broadband source. This is again where these 3D couplers will come in at some point. We need to encode the weights. This is a spectral shaper, also an instrument you can buy. You need to modulate quite fast, so electro-optical modulators you can exploit here. And now it is again matching very well to optics because these can be extremely fast. You can buy 110 gigahertz modulators or even faster ones, so very short time slots. This way you do not need very long fibers, which give you that dispersion and also loss. And then the addition is calculated each time slot at the photodetector once this is driven. And all, again, has to be run by a fast digital interface, but you only need to control one modulator. So this is the key thing. For the entire system, you only need one DAC and you only need one ADC, but you can still perform a lot of multiplications with the entire chain. So as long as you have enough wavelengths and you modulate fast enough, you will gain in the end. This is the first implementation in the lab. Again, yeah, we are back to our messy table. So the amplifier, the source, edge electronics, fast electronics for driving this. But this is always the starting point. And then there are some challenges once you start building. The first one is the dispersion of the fiber. So we can just buy a highly dispersive fiber. But what will happen is that different short signals will spread out in time. So that essentially means that these channels also overlap in frequency. And if you now add them all up in one particular time slot, you can see that some of the signals leak in there that you don't really want. So the linear dispersion of the fiber is an issue. Therefore, we need to make it nonlinear. And this we also did by a trick. So you do not use the same dispersion everywhere, but you just cascade different passive elements. This is why passive optics are very nice for these sort of games. And the way it works is basically that different signals are reflected at different positions along this waveguide. So blue one here, the green one here, the yellow one here. And then the output is again well separated, but they arrive at different times. So you have not linear dispersion anymore, but nonlinear dispersion. And with this system, you can also do classification. This is version 2 here, our setup that is now in a rack again, so it's a bit more clean, but still off-the-shelf components with fast electronics. And with that, you can do classification as well to categorize some cells. Okay, I think I'm running out of time here, so I'll skip this part. Sorry, Philip, for the digital twin, which is used for modeling all of this. But what I wanted to say before I stop here is that I think there is a lot of interest in this field, but it's also a field that is moving extremely fast and with extreme amounts of money. So this is just a selection of headlines from the last year or so. You can see some crazy ones like this unconventional AI that raised $500 million in just a few months. This works if you have the right CEO that is very well connected. Yeah. Or you know some people like Bill Gates, then you can also raise a lot of money earlier this year. Light Matter and Lightelligence are the two MIT startups that came out. Light Matter a little earlier, also worth $4 billion, so a lot of money. Lightelligence, the competitor from the same group, but sitting in China with 200 million, I mean crazy amounts of money, because nobody really knows how to solve this computing problem long term, and the bets are out of which platform will be there. Those are not all optical, but also other ideas. But nevertheless, I think there's a lot of opportunity, and this is why I think it's worthwhile doing it. And here I stop. I thank my group and you for your attention.
Right. Do we have questions? Yes.
Hi, great stuff. Lots of stuff on the table there. No question, when you describe the vector matrix and probably also this wavelength stuff, when you're doing the sum, it seems to be you're summing intensities.
Yeah, that's true.
That's usually a huge problem.
Yeah, so this is why we also like to work with maybe not the perfect sources. So we don't use lasers anymore, but some sources that have a degree of incoherence, which is in principle nice, because then you can buy cheap ones, so superluminescent diodes or noisy frequency combs, in principle, things that other people don't want. And if you delay them just past their coherence length, which is usually not too bad, on this order, they don't talk to each other anymore. So this we need to do.
That's not what I don't like, because you only have positive numbers to represent.
Of course, yeah. This is, of course, always the challenge, and we only can get negative numbers by doing a balance detection. So we need a second set, and then we do a difference in a balanced photodetector. Exactly. So we make basically two paths and then go from both sides into this balanced detectors and then calculate it directly.
Kick that to 100 gigahertz becomes a problem.
Yes, this is always, there are always technical challenges. But the 100 gigahertz, I think this is for the far future. So for being competitive, you don't need to be that fast. With 10 gigahertz, you're already in business.
In the far future, you'll be competing with 800 gigahertz.
Yeah, this, then we need some smart people to figure out how to do this.
Other questions?
Thank you very much for the great talk. I had a question about the second part, when you talked about the matrix vector, the vector, the scalar product essentially.
Mm-hmm.
So how large can the vectors be at the moment, and are there any? What is the limit? When does attenuation become appropriate?
So what we estimate is that you can build systems with about 1,000 wavelengths on a chip, really with technology that is already there. You need to build a multiplexer that can separate those, and you need to have the bandwidth to fit them all into a sort of a source window. But this is, I think, the limit that makes sense. Then, because you sort of play with the channel spacing, with the modulation frequency, with available bandwidth, and this is sort of where it ends. But if you work with 32 or 64, so very reasonable numbers, you get already to more than 10 or 100 tops per watt. So if you design your system right, you can be efficient very, very fast. This is not easy, but in principle, on paper, you can do it with stuff that is already there. And the trick is, of course, to show that it works this way.
Okay, so let's move on to the next talk.
Thank you.